I'm Netanel from Qedma, and I'll be sharing this talk together with Seiji-san from Riken, and we'll be describing our work for using error mitigation and HPC to push forward for quantum advantage. Can I have the clicker working? Okay, so we all know that errors and noise really constitute a huge problem for quantum computing. If you try to run, even on the best devices available out there, any quantum circuit with appreciable size, you'll see that you get very large systematic errors that get worse and worse as you increase the size of your program. Now, there's several ways to remedy this. Maybe the most well-known way is error correction. We also know that error correction requires a huge amount of high-fidelity qubits, which are not currently available on near-term devices. At Qedma, we're focusing on a different way to eliminate errors, and this is error mitigation. Error mitigation does not use any extra qubits. It does use, however, extra QPU time, and therefore is very important to make it as efficient as possible. So at Qedma, we are launching a software called QESEM. QESEM is a software for error mitigation and error suppression, which gives unbiased results at very large circuit volumes. I want to also stress that QESEM can be combined with error correction, and in fact, this shows you that the fault tolerance transition is not a phase transition, it's in fact a smooth transition between full error mitigation and full error correction. Now, it's really important to get unbiased and efficient error mitigation to actually get quantum advantage. Once you run your program with QESEM, you will get no systematic errors, and you'll get your ideal values as if you're running on an error-free quantum computer, and you'll get only statistical error bars, which can be reduced by running for a longer time. Now, an important message I want to convey is that error-mitigated quantum computation is approaching the point of having quantum advantage. And by quantum advantage, I mean that the time to execute a circuit with error mitigation is smaller than the time it would take to classically simulate it. Today, we're already almost at that breaking point, and with devices that are going to be available very soon, we're actually going to be very deep into this regime of quantum advantage. And in fact, this is going to be an exponential separation between these running times, and error-mitigated quantum computation will be performing things that are not possible with classical computers. Now, the second half of the talk will be presented by Seiji-san, and he'll show you our joint work for accelerating this timeline into quantum advantage. So first, I want to introduce our software in more detail. So this is the workflow of the software. It starts with a user sending our system the circuit he wants to run, the quantities he wants to measure, the accuracy level he demands, and the specific device he wants to run this on. Based on this information, we then run a characterization of the errors on the hardware, on the specific hardware, at the specific time we're going to execute the circuit. This is very important. We perform optimization of the quantum gates on that hardware. We transpile the circuit based on this characterization to obtain optimal results. And based on the characterization, we also compile the circuit into an ensemble of quantum circuits, which we then execute on the quantum hardware, collect back the results, do classical post-processing, and then return unbiased results to the user. Unbiased means that your algorithm runs as if it's being run on a noise-free quantum computer. I want to stress that point. Now, QESEM is also application agnostic, meaning that it works for any quantum circuit you want to run. And it's also hardware agnostic, meaning it can run on a variety of hardware platforms, and I'll show you several demonstrations. Two important numbers I want you to keep in mind, which basically quantify the benefits of using QESEM for performing error mitigation. The first one is something we call the circuit volume boost, and it goes the following. So you first set the accuracy level you want to obtain when you execute your program, and then you can ask, what is the largest volume of a quantum circuit I can run on a device as is without error mitigation? And what is the volume of a circuit I can run together with QESEM and obtain that accuracy level? If you take the ratios of these volume, you get the circuit volume boost, which can, for high accuracies, can reach a boost of 1,000 even more. High accuracies for example, required for chemical applications. You can also ask, what is the performance in terms of QPU time? And here we want to compare to the competing method for performing unbiased error mitigation, which is probabilistic error cancellation. And you can see that QESEM performs exponentially better and allows the user to access quantum circuits that are not possible to run using PC. Now, I want to share with you this demonstration. So these latest demonstrations that we performed, the first one was an IonQ in a collaboration with AWS Bracket. And here we ran a chemical application for the O2 molecule. We're running a VQE circuit with of the order of 100 gates on 12 qubits. And you can see in red the result we got for the ground state energy of that molecule if you ran it without error mitigation compared to the ideal value you would get for this circuit if you run on a perfect quantum computer with no noise in black. You can also see in blue what you get when you run the circuit on IonQ's device with our error mitigation, and you can see that indeed you get results which are accurately correct and within statistical error bars with the ideal results. You can see that this happens also for other quantities like orbital occupations and other correlations. Now, before moving on to the other large-scale demonstrations, I want to introduce a quantity which measures the complexity of error-mitigating quantum circuits and also the complexity of classically simulating them. This quantity is called the active volume, and in a nutshell, it's basically the number of 2-qubit gates affecting the observable you want to measure. So if you look at the diagram on the left, you can see a brick wall circuit and an observable being measured at the end, and you can see kind of a fan of the 2-qubit gates affecting this observable. Now, it's very insightful to look at these active volumes for circuits, for a family of circuits which are often used as benchmark and also simulate a physical model. This is called the Ising model. And these circuits are basically repeated layers of X rotations, Z rotations, and Z rotations applied n times. And at the bottom here, you can see how these active volumes look as a function of the circuit depth. And in the generic cases, the cases I'm going to show you, these volumes have the shape of what we call a light cone. So information is propagating in the circuit with a certain velocity. Now, the first demonstration I want to show you is a demonstration on one-dimensional model with 40 qubits. And in this demonstration, we ran deep circuits, and we measured various quantities like 2-point correlations and string operators. You can see on the plot of the right, as a function of the length of the string operator, we basically access higher and higher active volume, reaching up all the way up to a volume of 490 2-qubit gate in a circuit that in total had 1,400 gates and a depth of 72 layers. Okay? So this is probably one of the largest unbiased error mitigation experiments ever performed, and it's maybe only rivaled by these 2-dimensional demonstrations we did on a full device, a full Eagle device with 190 qubits, again reaching volumes of around 400, measuring various observables, and basically reaching an active volume that covers the full device, uses all the qubits in the device. Now, you can use these results to map out the roadmap for quantum advantage using QESEM by plotting the required QPU time to error mitigate a certain active volume here on the horizontal axis. And you can plot these QPU times for different fidelities, and you can ask when do these lines cross into the regime where these circuits are no longer simulatable. Okay? So, and you can see from these plots that already with fidelities of 3 nines, we'll be able to provide quantum advantage, we'll be very deep in this quantum advantage regime. And Seiji-san is now going to show you that by combining HPCs together with error mitigation, we can actually push these lines forward and actually considerably accelerate the timeline for obtaining quantum advantage. So Seiji, the floor is yours.
Okay, thank you, Netanel. Okay, thank you. One of the most promising applications that may have a quantum advantage is quantum dynamics. here, very recently, in our archive paper, we explored dynamics of kick-dicing model on a two-dimensional hexagonal, heavy hexagonal lattice using IBM quantum computers, which shows so-called discrete time crystal. Discrete time crystal, DTC, is a non-equilibrium state with spontaneously broken discrete time translational symmetry, starting with stripe-like states as the initial state shown in the left panel. We studied Floquet dynamics determined by unitary operator UF, which already introduced by Netanel. And of course, we fixed the Z rotation angle at particular values so that the dynamics is completely determined by the two parameters, theta x and theta z. And one thing that one should notice is that when theta x is pi, dynamics shows a trivial DTC. Because the Floquet dynamics is completely determined by the product of Pauli operators, and therefore dynamics evolves in time from 000 to 111 and go back to 000 state, and so on and so forth. And showing the period of 2 time steps. Therefore, it breaks the discrete time symmetry in time domain. In order to mitigate errors and noise in the real devices, we also introduced a heuristic rescaling error mitigation method, which is simply by dividing the experimental load data by those taken at the theta x equal pi, where a trivial DTC is expected. The experimental results with this simple rescaling error mitigation is shown over there by yellow diamonds obtained for 28 qubit using IBM Torino device. And there also we compare experimental results with the classical state vector method. You can see that the agreement is excellent up to like 50 time step, which is already significant. And even more, we did a similar comparison using a much more system of 133 qubits using a whole device of IBM Torino. And again, the yellow diamond shows the experimental result with this empirical rescaling error mitigations, which are now compared with the two-dimensional tensor network method with different bond dimensions, suggesting that the convergence of the classical calculations is good enough. And again, we achieved excellent agreement between experiments and classical simulations, which is really extraordinary because the size of the system is now more than 100 qubits. However, there are cases where this simple error mitigation method does not work, depending on the parameters and the depth of the circuit that you use. For instance, up there, for this parameter, the disagreement between experiment and state vector method are much enhanced, especially when the time is long enough. So here in this experiment, we choose a particular set of parameters with the fully polarized state of the initial state, a case where this simple error mitigation does not work. And in this plot, we measure the average of the magnetization of 28 qubits using IBM Kawasaki and IBM Torino. And red are the experimental raw data, and greens are the experimental data with this simple rescaling error mitigation, which clearly deviate from the exact values. Even for time step, like 5 time step already, they disagree. However, when we use unbiased error mitigation developed by Qedma, we can successfully reproduce these exact values, which are indicated by gray circles. Now, how we can combine classical and quantum computations to increase the number of steps that we can reach to make an average of expectation, to take an expectation value with given desired accuracy. Our main idea is very simple, to divide a total evolution time, large T, into two parts. The first part is treated using quantum computers, and the second half of quantum dynamics is treated classically using HPC. And all we have to do classically is to backpropagate the operator O for time steps tau, and measure O of tau over the time-evolved quantum state psi of T in quantum computer. And here is the demonstration of a hybrid classical quantum computation for characterizing model on a one-dimensional system of 20 qubits. And the horizontal axis is the total evolution time divided into a classical and quantum evolution time. And in quantum computer, we use IBM Kawasaki and IBM Torino, and classical calculations, we use a tensor network method to backpropagate the average of the expectation value, the operator, I should say. And the yellow is the experimental value of the magnetization, which is still away from the exact value denoted by gray circles. However, if we use unbiased error mitigation method, QESEM, one can again reproduce exact values indicated by blue. So what is the most beneficial in combining classical and quantum computations is we can significantly reduce the QPU time required to measure observable with a given statistical error. Doing systematic experiments for smaller systems using different IBM computers denoted by solid circles in the left panel, we can estimate with some confidence the required QPU time as a function of active volume VA in the quantum circuit over there. So blue is the required QPU time when you use no quantum classical computations, while this red indicates the required QPU time when you use classical computers with time evolution like tau equal to 20. Although that the required QPU time increases both exponentially, the active volume that enters in the exponent down there reduces as much as what you treated in classically, and therefore the required QPU time reduces. Just give you the example. Let us assume that we have a total evolution time large T 30, and if you don't use any classical computations, it requires over 800 minutes over there, assuming that you are averaging magnetization with the statistical error of 5%. However, if you use classical computers with 20 time steps, this required quantum QPU time reduces significantly down to 40. So this clearly demonstrates that combining unbiased error mitigated quantum computer along with the classical HPC can reduce its required QPU time, indicated originally by a yellow solid line to a yellow dashed line. And therefore, it can accelerate achieving the quantum advantage much sooner than later before entering the FTQC era. So please stay tuned because more results will be coming. Thank you.
Stay up. Thank you to both speakers. If there are any questions, please, again, put it on Slido. I don't think we have any yet, and we're a bit behind schedule, but I do have one question for the both of you. I think one common theme today from multiple speakers has been the idea of cross-border collaboration, multi-party collaboration. And I just wanted to ask both of you to maybe speak to what that experience has been for you and how important it has been for you to work together across organizations.
Yeah, go ahead.
Yeah, I think it's very important for us to understand, what our clients, what do they really need, what is important for them, and finding kind of the joint research project that would be aligned directly with what they're aiming for. And this collaboration has been super insightful for doing that.
Yes.
Yeah. So in order to use quantum computers very efficiently, we need someone like you, Netanel, to get good results.